oxygen here. So is it about conjugate base stability? No, it's not about the size of the atom, it is about this element that is next to it. And what this is doing is withdrawing electron density. So from this bond, making it more acidic. We call that inductive effect before. Okay? You have to know that for the test. Also, I explained to you the more oxygens you have, the more acidic it is, yes? And for a similar reason. Okay? Resonance structures may have something to do with it as well. Okay? Which of these two do you expect to be more acidic? CH3OH or CH3SH? Outstanding. CH3SH. Okay? Because the acidic proton is on which element? Is it on the sulfur or on the hydrogen? On this element or on the carbon?
No, it's the sulfur.
Maybe I'm not going to talk about this topic anymore. The acidic proton is next to the oxygen and the sulfur, not on the carbon, because the difference in polarity between the carbon and the hydrogen is 0.4. So that hydrogen is not very acidic. It is more acidic here because it is more polarized, yes? Now when you do lose the hydrogen, you will have this. And this is on a different element. The negative charge is on a different element. So which one is a better? This one, because it's lower in the period. That means it is in the period, no. In the group, that means it is more stable. Okay? I'm done with that. You appear not to have done anything this weekend. What you guys do this weekend?
So then that applies to all of them, right?
What do you mean that applies to all of them?
Yeah.
It applies to when it needs to be applied. It does not apply to all of them.
Right, but if the CL is more acidic because it's lower in the group, right? And the same thing with the S?
No.
The CL is not lower in the group, brother. The CL is higher in this group. But here, it is not the I and it's not the CL where the negative charge is. So that doesn't apply to that, because it doesn't. It applies to that because the negative charge is on the element that is lower. Yes? Ka times Kb is equal to 1.0 times 10 to the minus 14. Okay? So this is for the conjugate acid-base pair. So if I give you HF has a Ka, yes? Can I find the Kb of the conjugate base of HF? What's the conjugate base of HF? Minus F, yes? If I have this Ka, I can find that Kb. 1.0 times 10 to the minus 10, 14. Let's do a problem like that. Calculate Kb for F minus. So if I am asking for the Kb of F minus, I must have a Ka, yes? And the Ka is for the conjugate acid of this. Okay, so here you're given a Ka, and you need to find Kb. So Ka times Kb is 1.0 times 10 to the minus 14. How simple is this problem?
Just solve, yeah.
I almost don't even want to do it, that's how simple this problem is. Okay? Okay. Question here would be, is the following solution acidic or basic? Okay. This solution, NH4Cl, is it acidic or basic?
Basic.
You have to look at the ions that this forms, okay? Most of these will be ionic compounds. So this will dissociate into what?
Ammonium
NH4 plus
and chlorine.
and Cl minus. Now, question is this, what could this be? An acid or a base?
Base.
If this is going to be anything, it's going to be a base. And you have to know where this came from, okay?
Mhm.
And if it is something weak, it will be basic. If it is something acidic, it will be,
Well, depends on the
okay,
strength, no?
let's look at this one first, okay? So, where does this come from? This is the base, yes? It must have a conjugate acid. What's the conjugate acid of this?
HCl.
HCl. So, is this basic?
Neutral.
This is a strong acid.
Yeah.
And this is the conjugate base of a strong acid.
Just neutral.
And the conjugate base of a strong acid is neutral, or it has negligible basic properties. What it means is that it's not very basic, yes? So, this is not basic.
It's acidic.
How about an NH4 plus? Where did that come from? This came from NH3. Is NH3 a strong base or is it a weak base? This NH3 here, whereas that came from, this is a weak base. Because this is a weak base, what's that of this? The conjugate acid. Because this is a weak base. The conjugate acid of a weak base is acidic. So as a result, this entire solution is acidic. Now, I will always give you one that is neutral and the other one acidic or basic, or I can give you one that is both of them, both neutral. I will not give you one in which one is acidic and the other one is basic, because it's kind of weird. You can't decide what to do. How about this? Is that acidic? If I dissolve that in pure water, would the solution be acidic or would it be basic?
Neutral.
This is an argument I had with a biology major when I went to school. We were taking marine biology, and she said that ocean water is acidic. And she said it was acidic because of the Cl minus. So now you understand. Na plus and Cl minus. Does Na plus change the pH?
No, because it's group 1, right?
This is a group 1 cation, yes? Group 1 does not change the pH. So we're going to say this is neutral. Is this neutral or is it, what could this be? Could it be acidic?
We just said it was neutral.
I'm asking questions, answer the questions.
No, it's neutral.
No, I don't care if it's neutral or not. What my question is, if this were to be anything, what would it be, an acid or a base?
A base.
A base, and it would be a base because?
Conjugate acid is strong.
Because it has a negative charge, and things that have negative charges, when you look at them, not all of them, right? Not all of them. When you look at them, your guess is that it should be a base, yes? And then you know that this base came from HCl, and HCl is a strong acid, so this is neutral. Would that change the pH of the ocean? No. Her idea was that the conjugate acid of this is HCl, that this reacts with water, Cl minus, to form HCl, and HCl is an acid, so the ocean is acidic. She never tasted the ocean before. Does the ocean taste like vinegar? How does it taste?
So sour.
It tastes like bitter, yes, a little bit? Salty, huh? You said salty. No, either sour or bitter. Sour is acidic and bitter is basic. So when you take a sip of vinegar, how should it taste like? It is acidic, it tastes sour, yes? And everybody likes sour, nobody likes bitter. Okay? If you lick your soap, what would it be?
Oh.
You never tasted soap before? It tastes nasty? Why you be tasting soap? Okay, go to your house and lick the bar of soap and you will find out it is bitter, my friends. So go around now tasting things and find out whether they are acidic or basic. Okay, so that's neutral. How about this? Acidic, basic, or neutral?
So it's potassium and nitrate.
You have to split these, yes?
Yep.
One is potassium plus and the other one is
Nitrate.
NO3 minus. Okay? Potassium plus is from what group?
First.
This is group 1, so this is neutral. And there are degrees to this thing, okay? But so first approximation, neutral. And NO3 minus, acidic, basic, or neutral. Could this be acidic? Is it
Well, it
possible
has-
that this is acidic?
It has a negative charge.
Negatively charged most of the time, and it's next to something that is positive. So this is supposed to be a base. Now, is it basic? Is that basic? It is not basic. Why is this not basic? Because the conjugate acid of this is HNO3, and HNO3 is
Strong acid.
strong. What that means is that whenever you make HNO3, what is it going to do? It is going to dissociate. It is going to dissociate into that. So would this have a tendency to get a proton to become this? No, if it's going to
No, it wants to
dissociate,
do
it always wants to be this. It doesn't want to be this. So this is going to be neutral. This is sodium acetate. Acidic, basic, or neutral?
So that's a weak acid.
So this dissociates into what? CH3,
Acetate.
OO minus, and Na plus. That one's easy, yes?
Yeah.
Do you want to get sodium on the test or potassium?
Oh yeah.
Yes, so you don't have to think, yes? What is this? This is neutral. And this? This is basic. How do you know this is basic?
Weak acid.
Because the conjugate acid of this stuff, which is this, is a weak acid. In other words, this does not resemble anything in the strong acid list, does it? Okay, that is not in the strong acid list. Last one.
That comes from propane. That's a strong acid. Comes with strong acid. Basic. Basic?
Hello? Acidic, basic, or neutral?
Basic.
This K is K plus, and it is neutral. Why is it neutral?
Group 1.
Yeah, it is. Okay, group 1 is like the short way of finding out that it is basic, yes? But that the reason why is the conjugate acid or the conjugate base. This has a conjugate base, yes? And the conjugate base is potassium hydroxide. That's just in the strong base list.
Okay.
So its conjugate acid is neutral. Okay, but don't worry about it. It's As long as you know, group 1, okay. What's this? ClO2 minus. Is that in the strong acid list somewhere? Have you ever seen this, something that resembles that in the strong acid list? No. The conjugate acid of this is this, HClO2. And is that a strong acid or a weak acid? That is a weak acid. Okay, how do you know it's a weak acid? It's not in the strong acid list. So as far as you know, this is a weak acid, so this is basic. This solution here is basic. I didn't send you the slides, did I? No. Wow. Okay, whatever it is. Okay, this is what you have to remember. There is something called hydrolysis, and that means when you dissolve things in water, they could be acidic or basic. That depends on a couple of things. That depends on size increases.
What is the hydrolysis?
I don't know. Google it. Size increases. Let's say, let's not say pH decreases. That one increase. Solution becomes more acidic. Now this is the size of the metal. So this is for metal cations when dissolved in water. Did we talk about what a Lewis acid is? Which are examples of Lewis acid, incomplete octets?
Yeah.
Yes? Okay, transition metals. So when you dissolve these ions in water, and you're comparing two of them, as the size of the ion increases, it becomes more acidic. And as the charge increases, it becomes more acidic. So here's an example. I have that cation, and I have that cation. Those are metals, yes? And I dissolve them in water. Which solution would be more acidic? This one or this one?
I'll do that.
Whatever metal this is, with this positively charged, will be more acidic. The solution will be more acidic than that one. And let's say that now they are both the same size, so I can compare them, yes? And this is +3, and this is +1. This metal cation has a 3 charge, +3, and the other one has a +1. Which one should be more acidic?
+3.
+3 should be more acidic. Okay, it doesn't matter if they're kind of neutral. Okay, what matters is one will be slightly more acidic than the other. It's a comparison, yes? Yes? Of course, since knowing the size of the cations is a 1045 topic, I don't ask you on the test, okay? But I will ask you, if I draw a picture like this, I expect you to know, okay? I expect you to know which one is more acidic based on the charge, based on the size and the charge.
Okay.
Guys, yes or no?
Yes.
You want to go to the next chapter? Let's go to the next chapter. How many classes do we have left? Do you know?
3.
3.
3 classes?
Jesus Christ.
Really?
Next Thursday, then Tuesday, then next Thursday.
3?
4 including this class. Next Thursday is the last class. No final. No, Technically,
Okay, guys, here's how this works, okay? We have 2 weeks and then finals week, yes? Yes or no?
Okay.
Now, because this is the summer, if we need to come that Tuesday and me teach you material, that's gonna happen.
Yeah.
Because this is not like it's finals week, it's not finals week, it's finals day. You understand? So the day of the final will be the last day of the classes we meet. But on that finals, let's say week,
You want
if
us
we
to come
need to
Tuesday?
teach material on that Tuesday, we will come to class and we will teach the material. If I don't, I'll come to class and it will be a review, another review. You ask me questions, I answer them. If you don't have any, then you don't have any, you know it all. Yes? Okay, so we gotta move fast, yes? I wish we would have done a better job before, but my secretary never sent you this stuff. My secretary is not Mitch.
Everyone's looking at him.
Because everybody thinks he helps out, yes?
Now the
He's not my
spanking jokes got
secretary.
really weird.
Huh?
Now the spanking jokes got really weird.
That's right, but it's not, that's what I'm saying. So he's not my secretary, yeah. Okay, next chapter is called Additional Aspects of Aqueous Equilibria, okay? And I need for you to know a few things from this chapter. We are going to fly through the chapter.
Additional aspects of what?
Aqueous equilibria. We're gonna fly through the chapter. First topic it's called common ion effect. Common ion effect. The common ion effect says that when you add a common ion, solubility decreases. So here is acetic acid. And here is what it dissociates into. And by the way, yeah,
You said increases or decreases?
decreases solubility. I said decrease, yes?
Yeah.
Yes.
So, if I had a common ion, what side do you think the ion will be? Would it be on this side? Do you see any ions here?
No.
No. If I had a common ion, I will be adding what? A product or a reactant? I will be adding a product in this case, yes? And if I add a product, according to the Chatelier's principle, where is the reaction going to go? It is going to go reverse.
Yeah.
Okay? The reaction goes reverse. The reaction goes reverse. Forward means more soluble or higher percent ionization. Reverse means less soluble, lower percent ionization. So, the common ion effect says when a common ion is added, solubility decreases and percent ionization decreases. And this is a result of what? As a result of Le Chatelier's principle. Le Chatelier's principle. So let's say I have a solution of this, and I add sodium acetate to this solution. I have this solution, and I have this equilibrium, and I add sodium acetate. What am I adding?
Is the buffer the CH3COOH?
What?
The buffer is the CH3COOH?
No. I haven't talked about buffers yet. I'm still talking about this. So this is what? Is the Na here in the equilibrium at all?
Nope.
No. Would it change the pH?
Nope.
No. And CH3COO minus is in the equilibrium. So if I add this,
Yeah.
what happens to the pH of this solution?
That's a
Does
weird.
it get more acidic or more basic? Does it go up or does it go down?
Goes down.
Go down means more acidic. This
Oh,
becomes more acidic?
No.
No, if you're adding this and this is a base, it's not gonna become more acidic, it's gonna become more basic.
Mhm.
But you're adding this, and the equilibrium is going that way. And this is the one that gives you the pH, yes?
Okay.
So as you go that way, you use that up and the pH goes up, meaning becoming more basic, okay? And what happens to the percent ionization? Does it go up or does it go down? Percent ionization decreases when you add that, okay? Because this way was percent ionization, that way is not percent ionization. A buffer. A buffer, what's the definition of a buffer to my biology friends here?
Change.
Okay. Yeah, that's not the biology definition, okay? Resist a pH change when small amounts of acid or base are added. So, a buffer has a region in which it buffers, yes? If I have a glass of a buffer and I add a bucket of acid, should that buffer?
No.
No, because I mean,
It's a lot of acid.
it's for small amounts in comparison to the buffer you have, okay? So you do have a buffer in your blood, yes? Yes? You do? So your pH of your blood stays more or less the same, yes or no?
Mhm.
So if you eat something and something that is basic goes into your blood, or something that is acidic goes into your blood, then your body has to readjust the pH, yes?
Mm.
And it will get rid of whatever it needs to get rid of through your kidneys or through your sweat or through whatever it is, okay?
So if you eat an acidic fruit, your blood would kind of be temporarily more basic to compensate? Or?
Yeah, it depends, right? Because we have an acid in our stomach, and then in the intestines we have a base.
Mm-hmm.
So some of it will be neutralized there, but your pH of your blood may change a little bit, and then it will be readjusted, meaning that it will stay the same.
Okay.
Okay? But yeah, if you eat, I don't want to talk about this because we are here in front of the world, yes? But there are people that test their urine, okay? I have a specific example, I just don't want to say it. But there's people that are testing the urine to see if the urine is acidic or basic, and like that, they eat stuff, okay, to make their, what they say pH of the blood, either more acidic or more basic, and then they test the urine again. And if they're satisfied, they stop eating that thing that is adjusting the pH. So they're making their body work as far as the pH is concerned, because the urine will be acidic or basic depending on what you eat, yes?
Mm-hmm.
Not the other way around. You can't look at the urine and say, oh, it's acidic, so I'm gonna eat the base now. Or it's basic, so. But, you know, it's, inject HCl in your blood vessel and see what happens, okay? Video recorded.
The HDL challenge.
All right. No, don't do it, okay? All right. So, a buffer resists a pH change. What is a buffer composed of? A buffer is composed of a weak acid and its conjugate base. A buffer is composed of a weak acid and its conjugate base. So, if I have HF and I want to make a buffer with HF, what do I need to add to this? I need to add the conjugate base of HF, which is F minus. But as you know, F minus does not exist by itself, yes? Yes or no? No minus exists by itself. You need a positive to go along with that. So how should this look like? Well, it could look like F minus on the test, or it could look like NaF, okay, because it has to have a positive, or it could look like KF.
So anything that'll give the conjugate.
Anything that will give this conjugate base will do it.
Perfect.
Okay? Because here I have a weak acid and I have its conjugate base. Yes?
So the F minus is wrong.
Huh?
The F minus is wrong?
The F minus strong?
Is wrong.
No, I'm saying you might see F minus is what it is. But you might see F minus, or you might see any of these. Like a group 1 and F minus. How about this one on the top, acidic or basic?
Basic.
Huh? How do I make a buffer from that? What do I need to add? So this is like the base, yes?
Mm-hmm.
And I need to add the weak acid that is associated with that, which is this.
Okay.
Acetic acid, or whatever, you don't have to know the name.
Mm-hmm.
So I mix this with this, and that will give me a buffer. Yes? You want a difficult one? Yes or no? Because when they are difficult, you are being challenged, yes? That's what you think? Very good. Which of the following produces a buffer? Which of the following produces a buffer when added to let's say, let's do this one. Okay, which of the following would produce a buffer? Check if you're gonna miss this on the test. Which one? None of the above, yes? And you would get it wrong, of course. What? You get it wrong.
Wait, no.
Is this one?
That's what I thought because it was strong.
Okay, but by definition, this is a what? Is this a base or an acid? It's a base. You add a base to another base, nothing is gonna happen. Even though this could, okay, whatever. Sodium hydroxide, you don't know about it, okay? Sodium hydroxide, this is a base. To another base, nothing would happen. Now this, which of the following produces a buffer when added to this? I didn't say how much I added, yes? But if I dissolve this, this is what? Strong or weak?
Strong.
This is strong acid. And this strong acid, when dissolved in water, is going to form H+.
Mm-hmm.
Okay? How much of it is going to form H+?
A lot.
A lot, no. How much of it?
All of it.
100% is going to form H+. And this H+ will react with this F- to form HF.
Okay.
I can't do it to all of it. But if I have a little bit of HF, and this is indirect formation of the buffer, yes? The buffer is not a straight up buffer. It is, when you add this with this, it gives you the conjugate acid of this, making that a buffer. Okay? Yes or no? So you can form a buffer by adding to the conjugate base a strong acid. Yes? Okay, you want to try another one?
Yeah.
A one that is not so tricky, yes? And you got this wrong. And you got it wrong because it was challenging? Why did you get it wrong? Because I did not explain it before. Now, it wasn't called challenging, yes? Yes or no? Nothing should be challenging. If you don't know, of course you don't know. So it's not called challenging. Okay. The same thing, okay? When blah 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 is added, so that's what I have. Which of the following will make a buffer from that? Which of the following, when added, which of the following of this, when added to that, would form a buffer?
C.
Okay, that's right, sodium hydroxide. It is sodium hydroxide because this is an acid, this is another acid, and they're both strong acids, and
That's
this
a
is
strong base.
a base. And this strong base is going to react with this to form the conjugate base of that. So it will form this, and I already have this. Yes? So that will be a buffer.
So what I'm getting here is that if you have an acid to make a buffer, you need to add a base, and vice versa. No?
When you have an acid,
And you want to make a buffer, you have to add a base.
no. No, it depends what acid you have, yes? HI. Is this a buffer? HI and I minus, is that a buffer?
No.
Hello?
It looks like it to me.
No. You would need something that's positive.
This is not a buffer ever. Only a buffer if you live in what department?
Biology?
That's right. This is not a buffer because this is a strong acid and this is its conjugate base. Okay? It's not a buffer, it's only H+. H+ is the only thing you added there. This does not have any basic properties. Yes? How can it be a buffer? A buffer is composed of a weak acid and a conjugate base. This is not basic, so only acid. So that's not a buffer. But can I form a buffer from this? Can I form a buffer from that? No, you cannot form a buffer from this either because that is strong acid with a strong base. It gives you salt and water. And nothing happens to be there coming from anything that is weak. So that cannot be a buffer. Strong acid with a strong base, not a buffer. Can that form a buffer at some point? Yes, this can form a buffer at some point. At the beginning, I'm going to have HClO, yes?
Mm-hmm.
That's acidic. And the conjugate base of this is basic. So if I wanted a buffer, I just put a little sodium hydroxide and you're going to form this. And this is a weak acid and its conjugate base that will buffer. Hello?
Mm-hmm.
What do I need to add to that to make a buffer? Just tell me straight up, what is it that makes a buffer from that? Hello? You guys confused now? Yeah.
That's a weak acid.
It's too bad. You have to get some questions wrong on the test, yes? You can't have them all right. So here's your chance to get this one wrong. What do I add to this? This is what? Is this the acid or the base?
Nice.
It could be both because this is amphoteric, yes? So if I wanted to make a buffer by adding the conjugate base of this, what would it be? Hello? Conjugate base of this? CO3 2 minus. That will make a buffer. Okay? Now if this acted like the base, what would it need to have on this side? If this is the base, what do I need to have on the other side to make a buffer? The conjugate acid of that, which is H2CO3. So carbonic acid with bicarbonate will buffer, and bicarbonate with carbonate will also buffer. Those are the buffers you have in your body, in case you didn't know. Now, how can I form, from here, how can I form this? By adding what to it? Let's say by adding what? Because, I mean, this is simple, conjugate base or conjugate acid of that since it's amphoteric. What do I need to add to this to make this? A strong base, yes? If I add a strong base to this, I will form some of this. What do I need to add to this to form that?
Oh, weak acid.
No, not a weak acid.
Strong acid.
I mean, you could add a weak acid, but if I add a little bit of a strong acid, I will form this and I will have a buffer. Yes or no? So by adding a strong acid to the weak base, I can have a buffer. And by adding a strong base to the weak acid, I can make a buffer also.
Can we do another one?
And of course, those are tricky questions, yes? Tricky, is that what you call them? Buffer capacity, write this down. I'm not in the mood to write it on the board. I'm like a girl today. Not in the mood. What was I saying before?
Buffer capacity.
Buffer capacity. Buffer capacity is the amount of acid or base, that needs to be added so buffer capacity is the amount of acid or base that needs to be added before there is a significant change in pH. Open parentheses, 0.1 is a significant change in pH units, right? Of course. So, if you have a pH at 3.5, let's say 3.50, okay, everybody pay attention when you finish writing. I have a pH at a 3.50. Yes? And my pH changes to 3.57. Was that a significant change in pH?
No.
No, that was not a significant change in pH. My pH changes again to 3.67. Was that a significant change in pH?
Yeah.
That is a significant change. It's 0.1 units away, is a significant change. Anything after that will be disastrous. Okay? Like a huge change. Okay, buffer capacity increases. We have an exam next week, my friends. Thursday. On acids and bases, and this chapter we are doing now, outstanding. Buffer capacity increases with increasing amounts of the weak acid and its conjugate base. Buffer capacity increases with increasing amounts of the weak acid and its conjugate base.
So this is the last class of notes before the test?
No, the last class may be Thursday. I don't think I can finish this chapter today. So, what did I say?
Buffer capacity increases with increasing the amount of the weak acid and its conjugate base.
So let's say this is a weak acid and this is the conjugate base. And this is the amount, okay? So let's say that the amount, so question here is, which of the following has a higher buffer capacity? Which of the following has a higher buffer capacity? So which one of those or cannot be determined?
Don't you need something to compare it to?
What?
Don't you need the original? Doesn't there need to be?
No, there's no, it's not a comparison. It's which of the following has a higher buffer capacity. It's a comparison between them.
So even if there's not a significant change, you can compare them
Significant change in what?
of the buffer capacity. Well, the change in pH. No.
You don't know the change in pH of that. You only know the amount of conjugate acid and conjugate base.
Is it?
Okay, you ready? What do you choose? See, the higher the amounts of both of the weak acid and the conjugate base, the more it buffers, yes? So here, I have how much of the weak acid? That much. And how much of this weak base? That. Now, I didn't make this difficult. Most of the time, you have to add both of these, okay, to determine if they are kind of close. You have to add them both, and whichever one gives you a larger number, that's the one with a higher buffer capacity. But here is simple. There is more of those, of both of those, than here, yes? So this will be a, how should I call this? That will have a higher what? Buffer capacity. A capacity to do what?
To buffer.
To buffer. That means that it will resist the pH change more than anything else.
Okay.
If you add an acid to this buffer, what is it going to react with? An acid. You add an acid to the buffer, what is it going to react with?
Base.
The base. It's going to react with this. It's going to decrease this concentration. If you add a base to this buffer, what is it going to react with?
Oh, weak acid.
It's going to react with this weak acid. And of course, when it reacts with this, it will make that. And it will react with this, it will make this. Okay? And the buffer will stay more or less the same. Okay? Yes or no, my friends? Now, in order for you to determine the pH of a buffer, you're going to use the pH of a buffer. You are going to use an equation called Henderson-Hasselbalch. Okay. That equation says pH is equal to pKa plus the log of the concentration of the base divided by that of the acid. Now, how do we find the pH of a weak acid?
Ice chart.
An ice chart. That's right. How do I find the pH of a buffer? An ice chart. It is an ice chart that has something on the product side, yes? Or I can find it using this equation here. And this equation here has something to do with, don't worry about it. I may do the derivation later. I gotta continue moving on, okay? So we're gonna use that equation. I'm gonna do problems on the board, okay? Next class. Or maybe at the end of today. Next thing is called titrations. Now, first thing we care about titrations is how they look on a graph. So during a titration, what do you add? You have an acid and you add a base. Or you have a base and you add an acid. Titration is an acid-base titration, yes? So if I have an acid, the pH meter is inside the acid. and the pH here should begin where?
Very low.
Let's say this is pH, and this is volume of whatever added. So if I have an acid, and I'm adding a base to it, the pH should start where?
The bottom.
At the bottom. It should start like this. And you are going to add the base, and it will become more and more basic. On this thing that is going up here, you see this line going up? And the other ones are kind of flat. Halfway in between this line is something called an equivalence point. It's halfway. Now, if that equivalence point happens to land on pH 7, you can tell something about the strength of the acid and the base. If it lands on pH 7, that means that the pH was neutral when you had equal amounts of both, the acid and the base. Because that describes equal amounts of both, the acid and the base. So I had equal amounts and the pH is 7, which means that the conjugate acid must have been neutral and the conjugate base must have been neutral. So this is the titration when the pH is equal to 7. This is the titration of a strong acid with a strong base. So let's say strong acid with strong base. Or we can say strong acid versus strong base titration. So if you wanted to find out whether your acid, let's say you have an unknown acid, yes? You wanted to find out if it is a weak acid or if it's a strong acid. What do?
You check the equivalency point.
You do a curve. That means you stick a pH meter inside of this and you titrate it, adding drop by drop by drop by drop, and checking the pH. You make a graph. If the equivalence point, what's the equivalence point once again? How do you find this number? It's a halfway, yes? From here to here. The distance, halfway. If it lands at pH 7, then it will be strong acid, strong base titration. Yeah, you have a question?
Yeah. We wrote that wrong before, strong acid.
You put 2 hours.
Oh. You guys tripping, huh? That was just to see if I catch you. Strong acid, strong base titration. Now let's say I have this. And let's say let's say 7 is here. So what is this a titration of?
So weak acid and a strong base.
So
A weak acid, how do you know it's a weak acid?
well, it's above 7, so it's more basic, right? So that means that when you titrated it, it didn't counteract like.
Yeah, that's right.
The
I'm
weak
just
acid.
surprised. I mean, you've done it? No? Okay, very good.
It makes sense that if you, at the equivalence point, the pH is basic, then base is dominating, the base dominates.
Yeah, no, I understand, but I am not sure you understood it that easily. But some of you did, okay? Others didn't, so I'm gonna explain it, okay? This pH is above 7, yes or no? And this must be, is this basic or acidic? It's basic, yes? So this pH is basic. And it is basic because you have, let's see, you have a strong base and you have a weak acid, yes?
Mhm.
And this strong base will react with a weak acid to form what? Hello?
Conjugate, buffer. No?
No, yeah, a buffer, but the strong base will react with a weak acid to form the conjugate base of this weak acid, yes?
Okay.
And the conjugate base of a weak acid is? Hello?
Basic.
The conjugate base of a weak acid is basic. So the conjugate base of a weak acid is basic, so that means a pH above 7 is basic. Because when you have 1 mole of this base, at the beginning you're going to form a buffer, okay? But when you have 1 mole of this base and 1 mole of this weak acid, do I have any of this weak base?
No, all of it associated.
Hello? I have 1 mole of this weak, strong
Strong base.
I have 1 mole of this strong base, yes? And I have 1 mole of this weak acid. The strong base is going to do what?
Associated entirely.
It's going to dissociate entirely, but it's going to do what? It's going to react with this, yes?
Yes.
Because it's strong.
Uh-huh.
So all of the strong base will react with
Some of the weak acid.
with some, no. If I have 1 mole of this and 1 mole of that,
It reacts.
then all of the strong base is going to react with
All of the weak.
the weak acid. Am I going to have any strong base at this point when I have 1 mole of this and 1 mole of this? No strong base.
We're gonna use
Am I going to
all-
have any of the weak acid at that point? No, because all of this reacted with all of that. I have nothing of this.
Okay.
All I have is the conjugate base of something weak, which means the reaction is, the pH is basic.
So it's what's left over after those two neutralize each other.
Yes. Now, as I add the strong base to this weak acid, I'm forming this, yes? And now I have this, which is the conjugate base, which is basic, and the weak acid. So that is going to do what? It is going to buffer. And this is what's happening here. I have the weak acid. And as I add the base, it's not going up fast, right? What is it doing? This region from here to here
Buffer point.
is called the buffer region. The pH does not want to change because you have a buffer. And now when you start overwhelming this buffer, meaning you add more, it can't hold it forever, what's going to happen next?
You know that.
It's going to go up, okay? In this region here, was there any buffering here?
No.
No, there's no buffering there. That means that the acid ran out, okay? That's it, no more buffer. You killed it, or you killed yourself. How do you like that?
Good.
Let's do the last case.
Okay.
What is that, the titration of?
Strong acid, weak base.
That would be weak acid, strong base.
A weak base into a strong acid.
Weak base.
What?
Weak base into a strong acid.
Well, the bases dominate.
No, the acid is.
Guys, think whatever you want, but think something.
Oh yeah, never mind. It's below 7. Okay.
Everybody commit your thoughts to the answer to this problem and say, I am sure, I'm willing to give my thumb for this. You never want to give up your thumb, by the way.
Really important.
Because you're not going to be able to grab paper to what? It's devastating, okay, not to have a thumb. So,
Strong acid, weak base.
so what is this a titration of?
Strong acid, weak base.
Strong acid, weak base?
Yes.
Okay, you say this is a strong acid, weak base titration. Is that what you say? Okay. So, the strong acid will react with a weak base to form what?
A weak base will form a conjugate acid. Right.
Conjugate acid.
Uh-huh.
Conjugate acid of this
The
weak base, yes?
Mhm.
And the conjugate acid of a weak base, is it acidic or basic? It's acidic.
Mhm.
So, whenever I have
Cool.
1 mole of this strong acid and 1 mole of this weak base, will I have any strong acid? No. Will I have any of this weak base? No. All of the weak base will have been converted to the conjugate acid of that weak base, which is acidic. So the pH is below, pH less than 7 for the titration of a strong acid versus a weak base, or a weak base strong acid titration. You can say whatever word you want first, okay?
It's a great way to think about it. So you always think about that they have equal amounts and just whatever is left based on that.
Yeah, whatever is left is what is causing the pH to be low.
Okay.
So what happens if you titrate a weak acid into a weak base, or vice versa?
It depends who's stronger. But no one would do such a silly thing.
Okay.
No, not that it doesn't happen. I'm just saying, if you want to find out something about the reaction, yes,
You wouldn't do that.
you don't do that. Okay, but if you mix a weak acid and a weak base, you have to subtract which one ran out first, and then you have to use ice charts to find the pH of those with the Kas and the Kbs. A little bit of a mess.
Is 7 the standard?
What?
7's the standard, right?
What do you mean 7 is the standard? No, 7 is not the standard.
It's just what you
7 is neutral.
Right, that's what I'm saying. So why don't you use the graph to look for 7 and
Yeah.
Yeah.
Is
If
the
it's at 7, if the equivalence point is at 7, what is it?
neutral?
Neutral. If the pH is, if the equivalence point is above 7, it is weak acid. If the pH is below 7, it is a weak base. It's like the opposite, yes?
Is the
Hello?
conjugate always based off your weak, whatever's weak? Like we always
Yes.
reference like the weak base, the weak acid.
Yes, it is.
Okay.
Okay, so that's that. There's only 3 examples. There is no weak and weak, okay? Weak and weak, no. And this region here is what region? Is buffer region, as you have the base, yes? And as you add the acid, it does not want to change the pH, yes? Hello? It does not want to change the pH.
So what do you call the region at the bottom when all of it is consumed? Is it a buffer region?
It's not a buffer region. The region should not have looked like this. Should have looked like this. Because then the pH is whatever acid you're adding. Polyprotic acids. Polyprotic acids have more than 1 ionizable proton. More than 1 ionizable proton. Polyprotic acids have more than 1 ionizable proton, and you will have, write this down, you will have as many equivalence points as you have ionizable protons. You will have as many ionizable protons as you do equivalence points, or as many equivalence points as you do ionizable protons. So polyprotic acid, let's say I have this. I have this.
You ready?
How many protons does this polyprotic acid have?
3.
Oh, that's for me?
So you're making all of these.
So, what is it? How many? There is an equivalence point here in this thing that is sloping up.
Yeah.
There is another equivalence point here sloping up. There is another equivalence point here sloping up. How many equivalence points does that have? 3 equivalence points. How many ionizable protons does that have? 3 ionizable protons. So this acid should look like this. H3X.
Okay.
Okay, whatever letter it is, okay? Whatever it is with 3 ionizable protons.
Okay.
Of course. If it looked like that, what would it be? X what?
H2X.
H2X, okay? One ionizable proton here, one ionizable proton there. Yes? Very good.
We did one of these in the lab, but it didn't come out quite that nicely.
Because it didn't come out, it comes out okay. It's just not very clear. It's not clear like that. Okay? What else? What? Yeah, man, I said next class. You were not paying attention because you were talking.
Yes, because this is what ours look like. You could barely even tell there's actually water to it in this one.
Wow, that one's really
I don't know if the data's bad or.
No, you don't have enough data, that's the problem.
Mhm.
Because this is supposed to go flat here.
Right.
So,
Yeah.
in your lab it went like this.
No, it's 45 data points. Yeah.
It's supposed to go like that. Okay, in the lab. So here's one that is very clear, but this one is not very clear. But you can see here, yes?
Yeah.
And there is another one there. If you are lucky, what happened to you was this. These here, instead of changing the slope, it went like this. Okay, it went like that, and then it's not very clear, yes? So good luck. Okay, what else we were talking about? Let's talk about KSP. We're gonna do problems next class, okay? KSP, and this K means what?
Equilibrium constant.
Equilibrium constant, yes, for SP, and SP stands for solubility product. Solubility product, and this is how that would look like. Let's say I have this calcium fluoride is a solid, and I add that to water, and it will form Ca2 plus 2F minus. Do you agree? Yes or no?
Yes.
So basically a solid associates in
A
cation.
solid will ionize. Okay? I am going to call this KSP when that is a solid. And what is the equilibrium expression for that?
It's just a product because the reactants and calculus is solid.
Okay, yeah, this is a solid, so it is only concentration of calcium 2 plus raised to the first power, concentration of F minus, because there is a coefficient here of 2 raised to the second power. As you can see here, this is not going to be part of the equilibrium expression, so this is only going to be called solubility product. Solubility because as you go forward, this is means solubility, dissolved, and only products. Yes?
Yep.
And once again, how do you find the KSP, or how do you find the concentration of something that has an equilibrium constant? What do? Build an ice chart. Ice chart, ice chart, ice chart. So when in doubt, what are you going to do during the test?
Ice chart.
An ice chart. On the final exam, when you don't know what to do an ice chart. I'm serious. Some of you will come and say, Professor, I have no idea about this problem. On the final exam, you will say, what's this problem about? You never spoke about this, and I'm going to tell you, ice chart. And then you're going to get the problem right. Did you have a question?
Yes. Since this is equilibrium, does it mean that some of the ions go back into a solid?
Yeah, of course.
Yeah, it keeps going back and forth.
The concentration depends on the KSP. All right, so here's the equilibrium constant. Tell me, the larger the KSP, the what the solubility?
The greater.
The large. Ms. Rodriguez, how's it going? The larger the KSP, the what?
The greater.
The greater the what? The greater the what?
She almost
gonna
went
get away
off
with
class
it.
without it.
The greater the what?
The solubility?
Really?
What?
What was it that I was asking? Yes. The higher the KSP, the greater the solubility, okay? She just guessed it because the other one said it. She don't know. So, if I have a KSP for something, let's say compound X, let's say MX, and this is MY. This is a KSP. The KSP, let's say for MX is 1.0 times 10 to the minus 14, and the KSP of that is 1.0 times 10 to the minus 12. Which one is more soluble of those two salts?
The bottom one.
MY.
MY? Because it has
Greater number.
the greater. But it doesn't look greater. I mean, 14 is bigger than 12, is it not?
No, it's negative. So it goes
Oh, okay, the negative makes this smaller. Okay, very good for you. At least you know that much math, huh? You got an A in math, didn't you? How horrible, listen, you got an A and never learned anything.
That's because you become a robot.
Yeah, I know.
It's crazy.
Okay, so if, let's say I have this equilibrium, yes? You see it? I have that equilibrium. And I add this to it. What happens?
That's gonna.
Wait, no.
Hello? I have that equilibrium and I add this to it. What happens?
I'm tempted to say a buffer, but probably no.
No, there's
It's
no
just
buffer here.
It's just a common ion, so it goes back. Solubility decreases. No?
So what this forms is K plus and F minus. Yes? K plus, do you see K here anywhere? No, not part of it. But you do see F minus, yes? And you're increasing this amount here. According to Le Chatelier's principle, what happens? The reaction goes reverse, solubility decreases. What's the name of this? Common ion effect. Okay? Common ion effect says when you add a common ion, solubility decreases, it goes in the reverse direction. We are going to find the concentration after you do that through ice charts. What time is this class over?
15 minutes.
How much?
In 15 minutes.
9:40. Very good. Let's do a couple of problems since you guys are so excited about my class. Tell me the truth. Is it getting you sad that this class is almost over? Getting me sad. I wish I could have you for another 2 semesters.
Should have. I'll see you in spring. Knock on wood.
I will be alive, but I don't know if I'm gonna be teaching this. Next class you need. Ms. Rodriguez, do you want to come to the board and do this problem? Since you're conversing so much.
I'm not talking actually.
No? That is my dreams. Let's change this problem.
Is that 1.2? It's weird that I call acetic acid chiku.
What did you say?
Chiku. Acetic acid reads chiku. So it reads like that in my head. Is that weird?
I think your broken foot's kind of.
What does it say? Who's gonna take that rat?
Did you give it away finally?
It's really here.
That dog is no good, man. That dog is chill. It's like not doing anything.
Didn't the dude pay you $200?
You know, guys want to have an adorable dog. Want to have a mean dog. Look at that. Doesn't do anything. Doesn't bark. Doesn't chew on things. Okay, guys, what do we do here? We have to do a what? Ice
Full
chart,
chart,
yes?
yeah.
What do we need to do an ice chart?
Concentrations. Initial concentrations.
Initial concentrations, okay, we have that. What else do we need? We could have equilibrium numbers if I'm asking for Ka.
But you need a
I'm not
pH.
asking for Ka.
You need a
I
pH.
need equilibrium numbers. What else do we need, my friends? I'm disappointed. No pH. A pH is what I'm looking for.
Yeah.
Okay. Whatever, okay? Let's mess it up. What do you need? Initial concentrations at the Ka, you can find equilibrium concentrations.
Okay.
Or if you have initial concentrations and I give you equilibrium concentrations, what can you find? The equilibrium constant. Yes? So here we have initial concentrations and what else? And Ka. And I am asking for pH. And pH is an equilibrium amount found from the ice chart, yes?
Yeah.
Equilibrium amount for HF. I mean HF, no.
H plus.
I'm having a bad day again.
Actually, if you have the Ka, can you just use the equation you introduced earlier, the Hasselbalch, whatever?
Yes, but we're doing ice charts. You can, but we're doing ice charts. So, the concentration of acetic acid, what is it? This is in moles, yes? It's not concentration, but that divided by 1 liter is, so I'm going to say 0.3 molarity, please. Put on your paper, 0.3 divided by 1 liter gives you 0.3 molarity. How much H plus did I have? Hello?
0.
0 H plus, because there's no source up there. And how much do I have of this, CH3COO minus?
0.
It has been 0 so far, it's
But now we
not
have
0
0.4.
anymore. Because I added something else, and this something else has a sodium and it has that acetate next to it.
Mm-hmm.
So that concentration is this number here. So that will be 0.45 molarity. Is that clear?
Mm-hmm.
For those robots that were 0, 0, 0, 0, everywhere 0. It's not like that. It's not 0, 0 anymore. Okay? You guys are like the Terminators. Huh?
Okay, now I'm confused.
Because,
What are you confused about, man? Is this information is given to you from there, so I put it in, this information is given to you from there, so I put it in, that's it.
how come the sodium is dissolved already and the acetate ion from the sodium is dissolved and the acetate ion from the acid isn't?
What?
Then you're
So you already
overcomplicating.
have the acetate ion from the sodium is what you're saying.
That's what it is, I'm not saying that, that's what it is, yes. Of course, because that's a group 1 cation, yes?
It doesn't change.
100% of it dissolves.
Okay, fine.
Solubility rules, yes? Not girls' rules, solubility rules. Okay, whatever, you did not get the joke. So, minus x, this is plus x, and plus x. You robots, you will make a mistake when you become robots. So, this and that, minus x, x, 0.45. What do you mean minus x, plus x?
That was the test, right?
Okay, what are we looking for, my friends?
You're looking for H plus
I am looking for,
X.
I am looking for x. Because when I have x, I can do the minus log of the concentration of H plus. And that's x. So for me to find the pH, I need to find that H plus. So I am going to write it in the equilibrium expression. Ka is equal to what? Products divided by reactants divided by this, yes or no?
Yep.
I am going to plug stuff in. 1.8 times 10 to the minus 5 is equal to x and x. What is it? The concentration of H plus is what?
X.
X.
And now you have
And this is when the robots from before that were saying x squared all the time will make a mistake and write x squared here. Okay? Concentration of H plus is x. Concentration of CO3 O minus is 0.45.
Minus x.
No, minus x, no, plus x.
It's
Yeah.
negligible because K is
Right.
Is what? Negligible.
negligible.
What's negligible?
but
Because K is small.
Just giving you a hard. Negligible.
Negligible.
What is negligible?
It doesn't matter.
No, I'm not saying what is the meaning of the word. I'm saying what is negligible. What?
K.
K. Oh, the K. Oh, the plus X. The plus X.
The change is
The
negligible.
plus X and the minus. Yeah.
So divided by concentration of 0.30
minus X.
minus x. Okay, very good.
So now we can.
Now, if you knew any math, you would say that this cancels with this, yes? No. Now what you would say? This cancels. No. Some of you mathematical geniuses will cross this out on the type. You will. If you do, I'm gonna get a picture and show it to everybody, okay? So, now, with your current mathematical abilities, can you solve for x?
Well, you could.
I don't know.
Divvy it up, distribute.
I am not sure. You can bring that up there, multiply this times a number, and this times x, and this times that x, and this times
Yeah.
that x. That's gonna give you x squared, x to the first power, plus a number, yes? That is a quadratic equation. If you know how to do the quadratic equation, good for you. Now, since I don't know how to do the quadratic equation, we are going to look at this number and say this is small. Because that is small, we are going to do an approximation. And the approximation is that the change, okay, this whatever has plus x and whatever has minus x will be equal to the number, because the change was very small. Because the equilibrium constant is very small. Does the reaction go forward by a lot, yes or no?
No.
No, it doesn't, because that's very small. It mainly stays on that side, so the change will be small. So we're going to say that 0.45 plus x is more or less equal to what number?
0.45.
0.45. And we're going to say 0.30 minus x is more or less 0.30. And that is going to simplify our math to such an extent Look, that's what it did. And now I am finding x, so 1.8 times 10 to the minus 5 times 0.30 divided by 0.45 will give me x.
And I got 1.2 times 10 to the negative 5.
Which one?
1.25.
I have this here.
1.2
1.2
times 10 to the negative 5.
times 10 to the negative 5 what?
Molar.
Does that have units, yes or no?
No.
No.
pH?
I don't know, it's just.
It's not
There's no
pH. This is x. Look at it. X is
A concentration.
concentration. It is molarity. If it were Ka, it wouldn't have units, yes? But Ka was given to you without units before. That does have units. So what's that?
So now
That's
we need
x,
to
yes?
use negative log.
So I will do the pH is the negative log. Okay, let's write next to this that this is the concentration of H plus. Write that. That's the concentration of H plus. So this is the negative log of H plus. What is it equal to?
4.92.
Yeah.
Negative log of 1.2 times 10 to the minus 5 is what? 4.9?
Yeah.
Does 4.9 have units? No units. Okay, guys. Congratulations, you're gonna have another test next week.
What's your last one?
What's my what?
Where's the last one?
The last what?
The last one?
Oh, the last test? I don't know.